going to look at graphs again. Different. Well, in this case, it's a velocity time graph. And we're going to think about integrating functions of time now. So if I want to work out the change in displacement, I don't actually have to draw or work out the displacement graph, because we know the integral of velocity, if I go up a level, will be displacement. So I could just find the value of the integral. So from 0 to 4, if I was to integrate that, I would get the change in displacement. So the complete integral will be the change in displacement. If I wanted to know the change in distance, that's now like finding area. And so I'd have to split it up, because then it's important, positive, negative, and so on. When you're doing the complete integral, well, the negative will cancel with the positive and it'll work out displacement. But if it's distance, as I say, we've got to treat it like area, and we would break it up into its different integrals. Okay. And so similarly, we have our acceleration graph there. And so the change in velocity would just be the straight integral from 0 to 4, whereas the change in speed, we treat it like an area question, and we break it up. Okay, this is below, this is above. We want to find out the total area. So drawing derivative graphs, which is basically what we're doing when we're drawing velocity graphs and so on. So how do we work out what is the next one going to look like and things like that? So function would be like our displacement graph. First derivative is our velocity graph, and acceleration is our second derivative graph. But I mean, we can use these ideas for any derivative graphs that we need to draw. So if we have a stationary point on the original function, then we know that will become an x-intercept the next level down, so the first derivative, because stationary point is when the first derivative equals 0. If we have an inflection point, well, that's when the second derivative is equal to 0. So therefore, we have an x-intercept at the second derivative, which means it must have come from a stationary point. And so we'll have a stationary point in the first derivative and an x-intercept in the second derivative. If the original graph is going up, it's increasing, then we know the first derivative is positive. So velocity would be above the axis. And if it's decreasing, it'll be negative. That doesn't really help us much with the acceleration graph, but the concavity will. So when it's concave up, I know the first derivative will be increasing, because we'll end up with positive on the second derivative. So if the second derivative is positive, it must have come from a curve that was increasing. So original graph concave up, we know that it'll be increasing in the next level down, and then positive at the second derivative. And concave down would just be the opposite of that. So decreasing at the first derivative and negative with the second derivative. Again, if you recognize the picture, or you think you do. Remember, sometimes you might not be sure what it is, but if you can justify yourself in the working, you look at the graph and you say, well, this looks like a parabola to me, so I'm assuming this is a quadratic function, therefore my derivative graph will be a linear function. So if you explain it, then, because all they're really interested in is, do you understand the calculus? Do you understand how it works? So if you originally had a horizontal line, then when you had to integrate it, so if you had to go up a level, say velocity was a horizontal line, you had to draw displacement, you'd end up with an oblique line. Because your horizontal line has a slope of 0, so you must have differentiated a linear function to get a constant. But if you do differentiate it, it'll just become the x-axis, because if we differentiate the horizontal line or the constant number, we get 0. So if it was an oblique line, then we must have come from a parabola. So if we go up, it'll be a parabola, but if we differentiate it, it'll become a horizontal line. And if it's a parabola, then it must have come from a cubic. And we know it'll inflect at the turning point from what we talked about with in the last slide there. And if we differentiate it, we'll have an oblique line. So remember these things. Integration is equal to area. Okay. So on a velocity graph, total area will give you distance, whereas total integral will give you displacement. And on the acceleration graph, total area will give you speed, whereas the total integral will give you velocity. Let's have a look at some that have appeared over the years. 2003, they've given us a velocity equation this time. So we've got a velocity time equation, 2 minus 4 cos t. At what times during this period is the particle at rest? Oh, well, we just need to solve when is velocity equal to 0. So we have a basic trig equation. Cos t is a half. We know we're in quadrants 1 and 4. The acute angle would be pi on 3. So I know that in the first quadrant it'll be that acute angle, but in the fourth quadrant it'll be, well, 360, but we're talking about radians. So 2 pi minus the acute angle. So we have pi on 3, 5 pi on 3. So after pi on 3 seconds, and again after 5 pi on 3 seconds. What is the maximum velocity of the particle? Now, I think the mistake to make here is to go and use calculus. In this case, we don't need to use calculus. Right? We see that word maximum and we think, okay, I've got to find stationary points and what have you. But we've got a trig curve. We know what the curve looks like. We don't have to draw it, but we know what it looks like. It's a cosine curve. They're asking us, what is the maximum? How high up will this cosine curve go? So what is the amplitude of our cosine curve? Anyone?
4.
Thank you. We have an amplitude of 4, but we've shifted the whole thing up 2. Therefore, the maximum it could ever be is 6. There's our answer. Okay. I mean, it still would have worked if you differentiated it and found when stationary points were 0. But obviously, that's going to involve more work. All right, let's sketch our graph. It is a trig graph. We've already determined the amplitude is 4. It's shifted up 2, and it's upside down because it was negative 4. The period is 2 pi. So I'm going to mark off every pi on 2. So there's my axes. It's a cosine graph. Cosine normally starts at the top. This one is upside down. So we'll start at the bottom, but we've been shifted up 2. So there we are. We'll start at negative 2. Okay, so we go up and down, and there's my curve. Okay. Calculate the distance travelled by the particle between 0 and pi. So they want the distance between 0 and pi. Let me just go back to that graph there. Now, because they're talking about distance, I've got to worry about above and below. If they had said total displacement, I could just integrate from 0 to pi. Not a problem. I'm going to have to find that point of intersection here with the axes. So the x-intercept, I suppose, is the technical name for that. And then we'll be able to work out our integral. So that turns out to be pi on 3. Now, how do I know that quickly? Because remember, back in part A, we found out when velocity was 0. So that, in fact, was the intercept. So 0 to pi on 3 is below, so that'll be negative. Pi on 3 to pi is positive. It'll be above. So a little bit of integration there. Subbing in. Oh, almost there. What a beautiful answer. 4 root 3 plus 2 pi on 3 meters. 2004. So question 9. Interesting little graph. It's an acceleration time graph, you'll notice this time. Acceleration time graph. Write down the time at which the velocity is a maximum. Now, okay, I could integrate this if I knew the equation. They would actually give me an equation. Because they are straight lines, I could work it out quite easily. But there'd be 3 different equations for the 3 different lines. But I'm not going to use that because integration, remember, is area. So if we want to find the velocity of the particle when it is a maximum, we're saying when would the integral give us the biggest answer? So velocity, remember, we know is the integral of acceleration. So we're saying when is that integral a maximum? Well, it's going to be a maximum at t equals 2, because as soon as I go past 2, I'm now going to have a negative value. So it's going to start subtracting from that answer. So I know at 2, it's going to be a maximum. If you wanted to, you could think of it this way. Velocity is a maximum when dv to t, the change in velocity, is equal to 0. Well, dv to t is acceleration. Where is acceleration equal to 0 again? Oh, it's equal to 0 at 2. So you can think of it that way. At what time during this interval is the particle furthest from the origin? So I've got an acceleration graph, and we now want to find something out about displacement. When is it furthest from the origin? Okay, so it's saying when is displacement a maximum? Well, displacement will be a maximum when its derivative is equal to 0. Its derivative is velocity. So it's now saying when is velocity equal to 0? But velocity is the integral of acceleration. So it's now saying when would the value of the integral be equal to 0? So we want to solve that. Well, in other words, when is the area above equal to the area below? And because they're nice, neat, straight lines, we can work that out exactly. We just need to make the area of the trapeziums the same. So by symmetry, we'd end up at t equals 4. Right? Because the triangle from 1 to 2 would equal the triangle from 2 to 3. And so logically, because it goes from 3 to minus 3, so it's lovely and symmetric, that rectangle would equal the same rectangle going from 3 to 4. So that's where the value of the integral would equal 0. Okay? So that's when it's furthest away from the origin. All right, let's have a look at the 2000 paper. This is 2007. This one's a lot more interesting because it's not straight lines. We've got some curves in there, and it's great. It's a velocity time graph. And I did have to make some assumptions, I warn you, during this. Because again, we don't have the equations of what the curves actually are. But you'll see as we go through the solutions, I've made some assumptions. But again, when you're doing a solution, if you justify why you're doing it, then they know you understand the problem, and then they're going to give you the marks. So, velocity is constant once we hit time equals 6. Using Simpson's rule, because of course we can't integrate, we don't know the function. So Simpson's rule will allow us to estimate, because we have got some coordinates there. We want to see the total distance, or estimate the distance, travelled between 0 and 4. Now, they didn't say how many function values to use, because I guess that's kind of obvious, seeing we from 0 to 4, we actually only know 3 points on the graph for sure. So we'll use those 3 points to do Simpson's rule. So it'll be h on 3, remember the end ones, 4y the odds, 2y the evens. Mind you, we won't end up with any of the even ones, will we? Because we're only doing those ones. So there's my little table of values. I know 0, 2 and 4. So it'll be 1 times the end one, 4 times the middle one. 6 metres it ends up being. So approximately 6 metres. Right, it told us it's initially at the origin, during which time is the displacement decreasing. Remember, we're looking at a velocity time graph. So we know it's decreasing when the derivative would be negative. So it would be dx to t. Dx to t is velocity. So now we can look at our graph and say, all right, when is velocity negative? That'll be when the displacement is decreasing. So after t is greater than 5, that's when it'll be decreasing. That's when velocity becomes negative. So they now want us to estimate when the object returns to the origin. Remember they told us it started at the origin. So what they're really saying is, it's similar to that last question, when is displacement equal to 0? Well, displacement is the integral of velocity. So we want to know when the overall integral is equal to 0. So again, we say, well, okay, when is the area above equal to the area below? Just put the picture back up there so we can work out our estimate. Right, by symmetry, I at least know those two triangles are going to be equal in area. So I know they'll cancel out. So the question now is, when is my rectangle underneath the axis the same as under the curve? Which, remember, we estimated back in part A using Simpson's rule to be 6. So we want to know, when is the area of that rectangle? So, we have to work out area 4, I've called it. I know area 4 has to equal 6. But I know it's 5 one side. What could A be? Oh, 5 times A would work out a rectangle. So about 1.2. Well, not about 1.2. Exactly 1.2. But that's after 6. So 7.2 seconds. We'll add that onto the 6. We'll get 7.2 seconds. Now comes the real fun. We're going to sketch the displacement curve. All right, when I'm doing these ones, especially when they're not just straight lines, I like to draw them underneath or above each other so I can translate points down. So there is our velocity time graph. Underneath it, I've drawn the displacement time graph, marked in the key points that we've got there, plus the key points we just found. We found that 6 was the area under the curve, so that's going to be an important one. Now, where does 8.5 come into it? Why have I marked off 8.5? Anyone got a clue why I picked that?
Oh, that's the highest, greatest displacement.
Yeah. See, if I add on the area of that triangle, the triangle is 2.5, base times height. So I know I'm going to go up to 8.5. Let's plot some points to get an idea. So they told me the object is initially at the origin. Okay? So I'll mark that point in. We found out, using Simpson's rule, that when t equals 4, the displacement was 6. So I'll mark in the point 4,6. We also determined that by symmetry, when t equals 6, x equals 6, because the area of the triangle above equals the area of the triangle below. And as I said, the area of the triangle is 2.5. So in between, we must go up to 8.5. Okay. What else do I know? We also just worked out that after 7.2 seconds, we return to the origin. So I know I'm back down there. Okay. This is where I've done a little bit of, well, not guesswork. I don't know exactly what the curve's going to look like, but what I do know is the steepness of the graph. If you look between 0 and 2 and look at between 2 and 4, I think it's fair to say that between 2 and 4, the curve is steeper than between 0 and 2. So that means its velocity will increase at a greater rate, if you like. So I know it's going to cover more distance between 2 and 4 than it does between 0 and 2. This is where the guesswork comes in. I've just plotted a point which is below 3, because I know it'll cover more distance between 2 and 4 than it will between 0 and 2. Now, when t is greater than 6, velocity is a constant. So therefore, at least I know that's a straight line. So when I integrate that constant, I'll get an oblique line. So I've drawn my first bit in. There's the rest of it. Now, how did I do it? Between the point B and the point D, I have an oblique line. If I integrate an oblique line, parabola. So now I'm going to get that parabolic shape here. And here, going from 0 to 4, I just know it's some curve. I don't know its equation, but it's going to be some curve. So I've just drawn one in to make it look nice. Isn't that fun? Let's try another one. 2005. Displacement time graph again. At what time is displacement a maximum? So displacement a maximum. Displacement is a maximum when the area is most positive, if you like, or when velocity is equal to 0. So it's either going to be at 2 or 6. Now, if we use their idea about positive is better than negative when we're talking about it, then the most positive it would be at 2. Because at 6, we're going to start subtracting values. So at 2 is probably the answer they're looking for that. Okay. At what time does it return to the origin? You can see similar sorts of questions coming up. Okay. When is displacement equal to 0? In other words, when is the area above equal to the area below? Now, I'm assuming these curves are the sort of like similar curves. So it's like an odd function around 2, if you like. So what I then need to know is the area of the rectangle from 0 to 1. It's a tricky one to work out there. 1 times 2. Human calculator? 2. Thank you. All right. And look, the answer's there. So we're assuming that little area is the same as that little area there. By symmetry, it looks right. So the question now is, when will that rectangle equal 2? When will that rectangle equal 2? And look, its height's 2. Area is 2. Height is 2. What could its width be? Anyone? I say, anyone? All right. So, what is that width? And in case if you still haven't worked it out, despite my big hint there, 2W will equal 2. The width is equal to 1. All right, so returns to the origin after 4 seconds. 4 seconds. Now we're going to draw a sketch. Last time we had a velocity graph, we drew a displacement. Now it's going the other way. We've got a velocity graph, we want to draw an acceleration graph. So here's velocity. So again, underneath, I'll draw another graph, plot in some key points there. What have we already worked out? Well, let's look at the easy bits. Differentiate a horizontal line, in other words, a constant, you get... Oh, careful. We're differentiating now, not integrating. Differentiate a constant. 0. So we've got to be on the axis, yeah. So between there and there, we know we're on the axis. Okay. From 1 to 3. Look, I don't know what that curve is. But the rotational symmetry, I'm going to say it's a cubic. So if that's a cubic, then when I differentiate it, I'll get a parabola. So I've drawn that sort of shape in. Oh, it's below the x-axis. Why is it below the x-axis? How did I know to put it below and not above? Right. The curve is decreasing, which means its derivative is negative. So it had to go below. Now, I'm again guessing here, but I'm guessing that that shape's the same as this one over here. So if I've assumed that's a parabola, I'm going to assume that's also parabolic when I differentiate it. And so I'll get something like that. And this time it's above, because the curve is increasing, so its derivative is positive. Okay, that was a fair bit there, but getting those graphs right is kind of important. So.